Hi there. Welcome to a video lecture from Math 348. In this particular lecture, I'm going to talk a little bit about a power series example. And this is just a piece of an example that we've been working on in class. It's for Legendre's equation. And what I'm going to go over here is simply giving you a function and going through finding the Maclaurin series for it. And then I'll connect it up with some other pieces of the example a little bit later. Okay, so the function we're going to work on, as you probably see here, it's the function natural log of 1 plus x over 1 minus x. Now, while I'm talking about this, I'm going to get rid of my video panel and I'll come back and say hello at the end. But for now, let me hide my video and just focus on the screen. All right. We are working on this particular function, and I want to write down a series formulation for it at x equals 0. Okay, that's the Maclaurin series piece. And now we've done a few of these in class, but I wanted to go through this one. It's a little more involved. Now notice what I do first. The first thing I'm going to do here is I'm going to use log rules so that I can write the log of this quotient as the difference of the logs. So that's what you see in this first step right here. I'm going to rewrite f of x as ln of 1 plus x. That's the numerator of that fraction, minus ln of the 1 minus x. That's the denominator of that fraction. Now, the big piece after that is we simply want to use some of this calculus of that we know of already from Calc 2, where we write the natural log in this integral form. We've done it in class a couple of times, so you're probably not that surprised that we're doing it. So what you want to do is say natural log of 1 plus x is really what I get when I integrate 1 over 1 plus t dt from definite bounds here, 0 to x. Likewise, you can get exactly the same kind of expression with the appropriate minus signs if you integrate 1 over 1 minus t dt, and I'll let you go off on your own and verify that those are actually correct. Now, once we've made that step, which is a big one, now let's go through and use that same formula we've been working on a lot in class. Go back to your formula sheet, to your 1 over 1 minus x, or 1 over 1 minus u, as we write it in class pretty often. And now what you want to do is say, okay, I can take this expression and rewrite it as a series. And likewise, I'm going to take 1 over 1 minus t and rewrite that one as a series as well. Now, those we've done in class a lot. I'll just remind you of them and move on. But these are two big steps. The first thing I do is I take the initiative to say, I'm going to use some log rules. I'm going to rewrite those logs in an integral form of an integrand that I know I've got a series representation for, and then I plug in that series representation. Now, those are the big steps to begin with. After that, it's really just some fairly simple work. Oh, and let me make sure that I point out, once we've made this series expression substitution, now we have this interval of convergence over here that we're really thinking about for x values between -1 and 1. Those are the x values for which I can make this substitution, and that's based on the interval of convergence for those series. All right, so now once we get there, let me scroll up just a little bit. Once we get there, it's a simple matter. Remember, we've done this several times in class. We want to interchange the order in which we integrate and differentiate, right? So up here, we're integrating and then we're summing, not differentiating at this point. I'm summing. And then in this next step down, I'm going to integrate first and then I'll sum after I'm done. Now, once I do that, or why do I do that? Well, I do it because integrating polynomials is piece cake. And so I want to integrate the polynomials first and save the series piece until the end. And so I do my integrals. So now these are definite integrals. So I have bounds here. I have to make sure that I use them when I'm evaluating my integrals. So I integrate my polynomials, I plug in my bounds, and I get a nice form for each one of those things right there. All right, so I've got those two series, and you know what? It looks like they're very much the same. So I think I can combine them. Their interval of convergence is absolute value of x less than 1. So now let's combine these, and the x to the n plus 1s look fine. I have this 1 over n plus 1 in the denominator, so I've got a common denominator. So it looks like the only thing I really have to wrestle with is, how do I think about adding the minus 1 to the m with just the regular 1 up here? Because now I have to really think about, well, whether m is odd or m is even. Notice if m, the index, is odd, then -1 to that odd power, that's going to give me a -1. So when I do that, anytime I've got an m that's odd, that -1 will add to that +1 to give me a 0. So all of the odd index terms of this series drop out. And when m is even, well, that's -1 to an even power. That gives me a 1. That gives me a 2. So now I have this piecewise defined expression where I realize this series has a bunch of 0 terms. So I'm going to rewrite it. I'm going to rewrite it so that I'm going to think about my index m as being only even. So I write it as m equals 2k, where k is basically non-negative integer. And then after that, well, what do I do here? My k is still allowed to go from 0 to infinity, but now what goes inside this series is basically my m plus 1, or my 2k plus 1. And there's the 2. And then here is my power. And so my index always ends up just adding over these odd power terms, by virtue of the way that I've written all of my m's as 2k's. So that's a little trick that we hadn't seen before in class, but now I'm basically done. It turns out that I can rewrite the natural log function as this type of series with this particular interval of convergence. All right, I think that's about it for this video. You should see a copy of these notes online, so you'll be able to check those out and download them and look at them while you're watching this video. Thanks for joining me, and I'll see you in some other video sessions later this semester.